All right, acids. Special kind of a molecular compound that sort of acts like an ionic compound when it hits water. They're kind of weird, and that's why they get their own special naming system. Officially, they are molecular compounds, even though the way that they look is as if they are some kind of ionic compound. They are molecular compounds of hydrogen and something else. Now, when you get to Chem 30, you'll learn a little bit more and find out that, in fact, we can expand this definition. But for Science 10, what we can see is this is going to be all we need to have. So to start with here, acids are formed when a molecular compound reacts with water. So this is actually a chemical reaction, and they're going to form hydrogen ions as well as some other anion or negatively charged ion. Now, to look at a chemical formula and try to identify it, there's two types. They start with H, okay, so HBr, H3PO4, HNO3, or they end with COOH. So a couple examples here that you could see, and you could name all 5 of the ones on this page. CH3COOH, there's that thing that tells us it's an acid. This is a fun one here because it's actually got a COOH at the end, and it has an HOOC, or in mirror image, COOH at the beginning. This is a fun word, diprotic acid. It means there's 2 hydrogens that can go away and react with water. Anyways, so you can see here, either start with an H or end with COOH. That's how you can identify them just by looking at the formula. To identify them from their name is that they will have the word acid in their name. And if I would click in the right place. There we go. Okay, so lots of words. I've summarized it over here, but let's go through the words. Oxoacids. These things contain hydrogen and a polyatomic anion, which contains oxygen. All right, so there's a couple polyatomic anions that don't have oxygen in them, but for the most part, we're going to be dealing with the ones that do. We name by looking at the anion. Okay, so here's where knowing your polyatomics is really super helpful. So first thing, if it ends in the letters ATE, 8, means the acid name will be the first part of the anion name with the 8 changed to ic. A weird one is actually H2SO4. Look, SO4, oh, that's the sulfate ion. Okay, lovely. So now you'd think, oh, we change 8 to ic. That would be sulfic. But no. The wonderful people who make up these names have decided that sulfic sounds weird, and so let's change the rule to make it sound better, and this is in fact not sulfic acid, but sulfuric acid. I'm used to it, so I guess I agree that it sounds better, but it just, doesn't quite follow the rule. All right, HMNO4 contains the permanganate. Oh, there's that 8 ending again. The acid name then would be permanganic acid. And there, actually, it does follow the rule. The 8 just changes to ic, and this is an ic acid. What about this one? CH3COOH. Oh, look, it ends in COOH. It must be an acid. And this, in fact, contains an acetate ion, specifically an anion. Remember, anions are just negatively charged ions. The acid name then would be acetic acid. So again, this one follows the rule. The 8 changes to ic, and then we add the word acid at the end. All right, what if it contains the ending ite? Well, if it has the ending ite, the acid name will be the first part of the anion name with the ite changed to us. HNO2 contains the nitrite anion. Acid name then with the ite changes to us, becomes nitrous acid. HOCl contains the hypochlorite anion. Acid name then would be hypochlorous acid. So the ite changes to us. Lovely. And then acid at the end. So summarizing everything here, I can summarize it very quickly. If we have a hydrogen or hydrogens plus a polyatomic ion, anion ends in ate, we have an ic acid. Anion ends in ite, we have an us acid. So just to try one more, or two more actually, one of each. What if I have H2 SiO3? All right, so here again, you got to know your polyatomic anions, or at least recognize that I should go look for that thing on my table of polyatomic ions. SiO3, oh, that's silicate. Oh, it ends in ate. This is going to be an ic acid. And this is going to become silicic acid. All right, so we started with silicate. ATE would follow this. It becomes silicic acid. Looks like I am making up words. That many I's in one word just doesn't seem right, but it is correct. All right, what if it ends in ite? Well, let's look at another one here. Let's look at actually two. One that doesn't follow the rule. H2SO3. It's sulfur. I don't know what it is about sulfur, but people just don't like sulfur, I guess. SO3. See, okay, that's the sulfite anion. And then this becomes, you'd think it should be sulfous acid, and in fact it is sulfurous. It is still an us, but instead of just, right, this is sulfite, I-T-E at the end here. It just sounds better if I make it sulfurous acid. We've looked at nitrite there. There's not a ton of us acids that you're going to commonly run into. Sulfurous, nitrous are the two most common. And then we've also got things like hypochlorous as well. So we'll actually leave it with that one there, because beyond those two, there's not a ton that you're going to deal with. All right. And takes us to our other kind of acid. Mineral acids is an old name for them, also known as binary acids. This is just going to be a hydrogen plus a nonmetal ion. And these things are all named as hydro whatever ic acid. So some examples here. The ... is the name of the anion. So HCl, when it's dissolved in water, reacts with water, becomes hydrochloric acid. So the chloride, right, the ide becomes hydroic. H2S, hydrosulfuric acid. HI, hydroiodic acid. Remember that for all of the acids, they can also be named as aqueous hydrogen anion, and that until they're in water, they are not quote-unquote acidic because they don't have a pH. Because pH, as a scale, runs from 0 to 14, with 7 being neutral. Above 7 is basic, below 7 is acidic, and it measures the concentration of hydrogen ions in water, which means, obviously, these have to be aqueous. Acidic substances have a high concentration of H+ ions and a low pH. A pH of 3 is 10 times more acidic than a pH of 4. A pH of 3 is 100 times more acidic than a pH of 5, and so on. Basic substances have a low concentration of H+ and a high pH. And lovely. Comparing all of these hydrogen ion concentrations to distilled water. Obviously, pure water is this distilled water. It has 0 times as many because it is. Baking soda solution, seawater, eggs, pH of about 8, which means they're slightly basic. They have 1/10 the amount of hydrogen ions as distilled water. Toothpaste, somewhere in the neighborhood of 9 to 10. It's actually 9.9, so really close to 10. Milk of magnesium, which can be used as like a help an upset stomach. Household ammonia, you see it there. Soapy water, bleaches and oven cleaners, liquid drain cleaner, caustic soda. These are all, like, as we get up to, this end of things here, these are nasty things. You don't want to spill these on yourself. And they're not acids. They're super strong bases. As we move towards this end here too, right? Urine, milk, acid rain, black coffee. So, I mean, acid rain, I'm not too worried if that lands on my head any more than black coffee lands on my hand. I suppose if the, acid rain or the black coffee were both the same temperature landing on my head, it might hurt, but that's the temperature, not the acidity. Tomato juice, pH of 4.1. Again, might sting if you got it in a cut, but I'm not too worried about that. pH of 3. Here we're getting into like grapefruit and orange juice. Definitely stings if we get them in a cut. Lemon juice or vinegar, pH of like 2.9. Anything in this range here, it's not going to feel nice if you get these in your eye, but it's not even through your skin. And then we've got like pH of 1, hydrochloric acid secreted from the stomach lining. Yeah, that's not going to do good things to skin. Your stomach has a lining of mucus inside it, which actually protects it, but yeah. Battery acid, obviously quite a lot stronger even than that. And by the time we get down to this end of things here, once again, definitely problematic if we spill these on our skin. Anyways, more on acids in class tomorrow. Thanks.